This one says a 12 kilogram block is at rest. So if it's at rest, basically what that tells us is, so first of all, we know that we have force of gravity going down, like so. We have, again, we have our force of gravity in the y direction, force of gravity in the x direction, and we have some normal force. Okay. Just have these two forces, normal force and force of gravity. Right now, we know that from what we saw in the previous one is that this thing's going to accelerate down the ramp based on what FGX is. However, it's saying it's at rest. If it's at rest, it means our acceleration must be 0 meters per second squared. That means our net force must be 0 newtons. So there must be some force of friction that is matching our force of gravity in the x direction. So if we look at sum of the forces in the x direction, it's equal to mass times acceleration in the x direction. And we know that FGX is trying to pull this thing down the ramp, but force of friction is saying, no, you're going to stay right where you are. Because at rest, this is why it's static friction, not kinetic friction. So because it's at rest, we know acceleration is 0, this becomes 0. So you get 0 is equal to FGX minus force of friction. But we know that force of friction is equal to the coefficient times normal force. Where normal force does not simply equal to force of gravity. In this case, when we have the inclined plane, normal force is equal to FGY. So we actually have to look at the sum of the forces in the y direction before we proceed. So you say, okay, MAY, we know it's not accelerating in the y direction, but we can see from our picture that our y is that perpendicular to the surface. Normal force is up. That's being opposed by the force of gravity in the y direction. So from here, we get 0 is equal to Fn minus force of gravity in the y direction. So if we solve for this, we get Fn is equal to Fgy, which is going to be mg, that's force of gravity, and it's going to be the cosine component of force of gravity. So this is what Fn is equal to, the cosine component. Now we can go back to our x direction. We said, okay, we're trying to solve for the coefficient of static friction. So we rewrite this one. We get Fgx is equal to force of friction. Let's write that out. We have force of friction is equal to Fgx. All I did was move over that force of friction over. And the coefficient of friction is going to be mu multiplied by normal force, which we just found to be mg cos theta. Fgx is mg sine theta. Look at this. We see that mass is on both sides of the equation. Gravity is on both sides of the equation. And if we divide both sides by cos, we get mu is equal to sine theta over cos theta. And that is what our coefficient of static friction is going to equal to. Some of you are in grade 12, you may have learned trig identities. Sine theta over cos theta is the equivalent to tan theta. So we get the coefficient of static friction for an object resting on an incline is ms tan theta. So if I now plug in the 40 degrees, tan 40 is equal to 0.839. That is our coefficient of static friction required between the block and the incline in order for it to not to move. So when we actually get this, it's not actually just 0.3, it's greater or equal to that value. So we actually don't know, is it 0.839 or is it bigger? But this is like kind of like the minimum. This is the minimum amount of required static friction required to keep this thing not moving.